towards infinity, as positive infinity, excuse me, as n gets larger and larger and larger, this scenario, 1 plus 1 over n to the nth power, is approaching 2.7 blah, 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 blah. Okay? It's kind of like, it's a non-repeating decimal, so it's just like pi, where it just is continuous. The, excuse me, this natural base, this value of e, you can see how it kind of mirrors the idea of what we did yesterday with that 1 plus your rate over n to the n times t. It mirrors that idea of that. We use this value of e, to, when we do compounding interest. If it's compounding monthly, quarterly, we use what we did yesterday. If it's compounding continuously, like it's always creating more and more and more, there's this e value that we use. There is a button on your calculator for this. All right? There is a little lower cursive e. But what we use this for is that, excuse me, is that we can write it in terms of exponents. All right? This value of e can be treated just the same way as it was a variable. It was e cubed, or x cubed times x to the fourth. What does it become?
X to the 7.
So in this case, it's e to the third, e to the fourth, so it's
E to the 7.
e to the seventh. Okay. So these exponent rules apply when you're working with e, because e is a variable. I don't want to say it's a variable, but it is its own value. Okay. Yes, sir.
What is it again?
What is what?
Second. It's the second
The-
and then the division.
Second division. All right. Same thing on the next one, where you have 10e cubed over 5e squared. What do you get?
2e.
Or not 2e. That's the question. Yeah.
Did you make that one on purpose? Did you just say that?
No, I just made that up off the top of my head.
Nice.
Wow.
That is talent.
I am something. Now you've got parentheses raised to an exponent. What do you have to make sure you do? Yeah, you got to remember to distribute out your exponent as you go through that. So you get 9e to the negative 8x. Excuse me. When you're dealing with the e as the exponent, yeah, I can't get rid of the signs. The reason that it is all right that we wind up with this negative value in your exponent, because it's going to show us something. It actually tells us whether or not it's growth or decay with the e. It is extremely easy to work with these things, guys. I don't want you to think that it's scary. But if you are just purely simplifying something like this versus graphing something like this, there's a slight difference in what you have to do. When you simplified expressions before, did you want negative exponents? No. So what would I have to do here?
Put it down.
What would I put down to the bottom? The e. So this would wind up being 9 over e to the 8x. The reason, the difference between a simplifying versus graph, if it asks you to graph the problem, you can leave it as a negative exponent, because that's telling you something about the graph. And I'll show you that here in a second. What happens is, this value of e, when it has a positive exponent or a negative exponent, the graph follows the same thing as exponential growth or exponential decay. That's all it is. Graphing these things is a little bit more complex, because you really can't find a lot of set of points like we did with growth and decay. We were able to use -2, -1. Because the value of e is some funky decimal, it's very difficult to substitute and crank that out by hand. So you probably won't have to graph these by hand without the use of a calculator. All right, does that make sense? Oh, oops. We'll do graphing after this. You guys already know where the button is in your calculator if you have to figure out what the value is. There will be times when we will use this e value within equations, so you might have to press a button. I know it's difficult.
So,
I'm asking a lot.
so how much should we run?
Usually I go a couple of decimals, so what was it, second, division,
And then just
7.39?
alright.
That's usually my rule, is to go to 2 decimal places, unless it says something else.
So can you look at
I'm
so can you look at
No, you gotta know what. You gotta know the whole number. You gotta memorize it.
Yeah.
And then you gotta learn to.
836 534 723 981 11652 673.
Oh wait, do you know that or you?
I did BS my whole way through that.
Hey, you know
But
what
I sold it.
Yeah, exactly, because all in the confidence.
Like, I wait, did that?
You guys ever heard of a guy named Eddie Izzard? Comedian?
Yes.
You know? Eddie Izzard, a British comedian, does a routine where he talks about it's not what you say,
With
it's
the national anthem.
not the national, the I am a donut one.
Oh, okay.
All right, where it's not what you say, but it's how you say it and how you sell it. So you can the JFK thing, we said ich bin ein Berliner. I guess he actually said it, I'm a donut, not I'm a Berliner, in the way it translated out. But he said it with such ferocity and everybody was yeah, and like well, he really just said he's a donut, but he believed it. So it's
they were all cheering this.
I wasn't there, but I'm sure they were. I do recommend, I highly recommend the watching. I think it's called Dress to Kill. It's a stand-up that he's done. You probably can find it on YouTube. It's very funny. I don't think I've seen the national anthem once.
He says it doesn't matter how you sound, you just have to like.
Oh yes, yes.
Yeah.
Oh, and then they talk about how when you're singing 12 Days of Christmas.
Yeah.
Everybody just jumps in and yells, "Five Rings!" And nobody knows the rest of the words.
Yeah.
But everybody loves that part. Exactly. But it's how you sell it, and that's kind of what it goes. But I totally recommend it. It's a good hour and a half of your life. It's a good time. So when we talk about graphing these, what I want you to remember here when we're dealing with graphs, it's extremely easy to tell the difference between a growth and decay when you're working with E. When you're graphing E, we're going to use this form. I'm not writing, don't write all this junk down, okay? What you want to know here is basically just this. This information is all you need to know out of this long, big, giant, annoying paragraph. Why not just say the following? When you have A times e to the rx, R is your rate, X is your variable. A is still your, what do you think A is going to be?
Your initial.
The previous multiplier.
Y-intercept. It's your Y-intercept. Your A value is still going to be your Y-intercept. Because if X is 0, what's R times 0? What's e to the 0?
1.
What's 1 times A?
A.
There's your Y-intercept.
Okay.
So when you're graphing these style problems, the only real point that you're able to find is your Y-intercept and knowing the direction that it's going to go. Okay? Yeah, Mike.
So we're gonna have to shift these.
Great question. Yes. Because what's nice about it is that not only can you do this, but if you throw in the idea of the shift, let me move this up, where you have Y equals A times E to the R, X minus H, think about it like that. Let me put this in parentheses, plus a K. What becomes your horizontal vertical shift? HK. It's the same idea. Where's your new, and these guys still have an asymptote. Where do you think your asymptote's going to be? Okay. Yep. Yeah, that's how they write it. They write it out as the X minus H will be in parentheses in that exponent. Okay. You still have the same exact idea. It matches the same growth or decay function. It pairs along with it. But your B value in this case is E. E to the R is your B value. Yes, sir?
Wait, why is your asymptote with A? Did you say the?
No, I said the asymptote with K.
Oh, okay, my bad.
It's okay.
Well, so it's still A is negative.
Yeah, it follows the same rules. Follows the same rules. Okay? It is very, very easy to walk through these things. Plus, remember, when you're graphing these, you're only going to be able to get one really ordered pair, and that's going to be your Y-intercept, and shift it off the Y-intercept. After that, it's a matter of remembering which direction things are going. You're gonna have a calculator. I can't get you guys to graph these things without a calculator, because the ways that the E value works, it is such that, I'm not gonna ask you to multiply by, I don't even remember what E is, was it 27 or 217 or something?
2.7, 3468.
Who do you appreciate?
Yeah, I think all the
Yeah, that is Yeah, you didn't have as much confidence in that last. You didn't sell it. All right. So, like I said, working with E values is relatively easy. Okay. Let me show you this. If I wanted to graph this, I have y equals 2 times e to the 0.25x.
75.
I'm sorry, 0.75x. Reading is hard.
That's why you teach me.
That's exactly right. Now, in this case, my value of r is a positive or negative? Positive, so it means it's following exponential growth. Okay. Now, my a value in this case is 2. So, where's my y-intercept?
2.
2. Is there a shift to this problem?
No.
Nope. I know it's got to go here. I know that the original graph here is a k value of 0. So where's my horizontal asymptote? 0. This being a growth function, I know it's got to do this because it's positive. You agree? So basically, it's doing this. Could you go to your calculator and get another ordered pair? Well, what's the point? Well, the point would be somewhere on the graph, I hope. It's really easy. 2 e to the 0.75x. If I just go right to my table, I have it at 0 and 2, 1 and 4.234.
You can write that down.
So it's just increasing a little bit more than I had anticipated. It looks like that. Yes, ma'am.
Wait, how do you say it wasn't going the other way?
What's my value of A? Is it positive or negative?
It's positive, so I know it's growth, but there's like 2 different ways to do that.
Remember, growth that was positive was going this way. If it was negative, it was going the other way.
Well, how do you know it's growth then?
Because the 0.75 is positive. Okay. The R value, remember, when it goes into these things, if the R value is greater than 0, it's growth. If it's negative, if it's less than 0, it's decay. And then it goes back to the idea of what's the A value. If your A value is positive, remember it's going, and then A negative is going the other way. All right, does that make sense, Izzy? Same idea if I want to throw in something with a shift. Oops. I didn't even do that. Weird. If I wanted to throw in something with a shift, what would be my parent E graph here? Okay. So my parent would be y equals 1 times e to the negative 0.5x. Would be okay with that? That would be the parent version of that?
Yeah.
All right. Where's my y-intercept?
1.
It's at 1. Is it growth or decay?
Okay.
It's decay. Why is it decay?
It's the negative R value.
Negative R value. So that means since A is positive, this is going to go from right to left, moving upward. You okay with that? Now, if I want to get a secondary point on this, put that in my calculator to find the next value. So this was e to the, what was it, negative 0.5?
Yeah.
Go to the table. So at negative 1, it's at 1.65. So I know that I'm working on some things I've liked lately. I know it's doing this. That's my parent function. To those points, what do you have to do?
Shift.
Which way?
Right 2, up 1.
Perfect. Those points all get moved to the right 2 and up 1. What do you do with your asymptote?
Move it up to
That's all it is, guys. It's the same exact idea. What I'm going to ask you guys to do when you're graphing these, if there is a shift, put your parent in, put the shift in. Give me 2 points on the curve. Give me the original parent's y-intercept and some other point from your table. And then when you shift it, just write those down, whatever the new shift is. I got it.
Do you want us to like write the ones out there?
Yes, please. Yeah, it's very simple to do, and it just, by doing that, it's just going to force you to slow down, put all values in, and then tell me where the y-intercept, or not the y-intercept, the horizontal asymptote goes. Okay? What's my domain and range? My domain is what? The domain is all real. What's my range?
All real more than one.
Perfect. Okay. Very, very, very straightforward. You see how it mirrors the idea of the exponential growth and K models that we graphed before? And those weren't tough. Yes, ma'am.
Is it all real and negative?
Yes. These guys still have these guys will have domains that are not bounded. We won't, because there's no vertical asymptotes. We'll have vertical asymptotes when we get the logarithms in.
So, but like for these problems, domains always going to be
Speaking of towards the end of the week, the way that this is working, because you guys are really kind of flying through this a little bit quicker than I anticipated, we're going to quiz 81383 Thursday.
Oh.
We'll start logarithms then Friday, and then finish logs next week. All right. That'll get us, the way I'm looking at it, is we have a full week next week, then the following week is the 3 full days and a half day. We'll probably wait to the test of that at 1 week, where we'll be that Wednesday will be the full day test, then the half day will be the non-calculated.
Okay.
I think that's what, we're just pacing it out last hour, and it looks like it's going to work just fine for that. Yes, ma'am?
Say you aren't going to be here on Thursday.
We're going to take it on Friday.
During class, you like
Yeah, we'll just have to kick you out. What's up?
Wait, so is it wait, like 3.5 weeks?
What?
Like
3.5 day, 4.5 day weekend?
3.5 day like week? Is it like next week or like the
No, it's a couple of weeks.
Okay.
It's a few weeks
It's,
out.
yes,
Yes, sir.
Is your range 12?
A value?
Yes, sir. Yep, your range is still bounded by K, and it's still dependent upon the A, whether it's positive or negative, it's going up or down. It mirrors growth to K exactly. It mirrors it exactly. It's just easier to graph because I'm not making you doing it by hand. Okay. Question on that. So where this comes into play then is working with the difference between compounding interest monthly, quarterly, and stuff like that versus compounding continuously, where your interest is always accruing. It's constantly accruing, not accruing at specific dates and checking it once in a while. It's just got a running tally to it. This is where they use this PERT formula. It's not because they have dandruff. It's funny because it's funny. Again, P stands for your principal, it's your initial amount. E is the button on your calculator. R is the rate as a decimal. And T is in time. Generally, I'm talking about time in years. The difference between this problem and what you did yesterday for the interest problems is that it'll say compounding continuously. If it is continuous, then you have to worry about PERT.
Do we need to talk one above it with the division thing?
No, that's what you did yesterday.
Oh, alright.
All right? That's what you did yesterday. This is you.
What's principal?
Principal is your initial amount. Your initial, what you started with. Yes, ma'am.
What does the thing for R say?
R, it's percent as a decimal. Sorry, my handwriting.
Oh, as
I thought that was
decimal? I thought it said of
I
decrease.
thought it just said S.
There. Your R value is some percentage as a decimal. Okay. You'll see how easy these are to work with. I mean, if you had no problem with the stuff from yesterday, these are even easier.
Alright.
Let me show you an example. Oh, I forgot to erase that.
1,083.29?
I don't know, I forgot. I don't know what happened to it. So if you deposit $1,000 into some account that pays 8% annual interest compounded continuously, how much do you have after a year? Well, let's make it after 10 years, because it's more fun. We're thinking big. Okay? See how it's worded just a little bit differently, where it says compounding continuously as opposed to compounding quarterly? That's the main difference. That tells you which formula to use. Okay. So it says continuous, you want per.
Can we multiply the E in there? Or?
Yep. So it's P e to the R times T. Your principal in this case was 1,000. E to your rate. 8% as a decimal is how much? 0.08 times 10. So, oops.
That what?
Bless you. Oops, I didn't need to hit that button. After 10 years, you've got $2,225.54.
Let's go.
Do you want to make that more difficult?
Ow.
Wait,
Don't know.
minimize the-
Oh, I thought we shifted. You had a way to make it. That's it.
No, just like in that number you guys were talking about yesterday, that number 62 where you had to solve for your initial principal, sometimes you have to do that.
Oh, all right.
And that, all that was just dividing out by the ER to the T on the side.
Just really just solve for you.
Well, whatever. We're all right? Yes, thank you. Quiz on this stuff will be calculator, non-calculator. So you'll have, I'm guessing, a graph or two they have to do, and then calculator stuff.
All right.
It would probably be more stuff, because this you really kind of need a calculator.
So what would be on the non-calculator?
That was
All right, try this one. Endangered species. We are all part of the U.S. Fish and Wildlife Departments. They keep a list of endangered species. Between the years of 1972 and 1998, the number of species could be modeled by the following blah, 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 where T is the number of years since 72. So your year 0 is 1972. So if year 0 is your 1972, what was your initial amount of species?
119.
How does that?
I did half an animal.
It's 0.6 of a species. Jeez.
Gosh, Cullen.
You guys gotta get that right.
Did I cut something off? Maybe it was like in thousands.
Yes,
I don't think-
looking for it.
It happens. Maybe there's like a live animal inside another animal. Maybe like a crocodile. They stuff.
It's been around for a while.
It makes sense, alright? You know those snakes?
Now let me ask you this.
Maybe like it's.
If your year 0 is 72, your initial principal was that amount, 119.6. Science, yes, exactly. Now, see how it's telling you to graph these? Again, I'm not going to have you graph these, but if you wanted to see how many there were when number of species reached 1,000, yeah, this has to be in the thousands. Nah, whatever. Number of endangered species reaches 1,000. What you do is just go right to your
Maybe
calculator.
it's 119.6.
Yeah.
Oops. What was the decimal value for the E? 0917.
Why aren't you?
Now, they're asking you to figure out when, after how many years did your species wind up at about 1,000 of them? Well, you're just scrolling through looking for the Y value to get to 1,000.
That's a lot of scrolling.
Sounds like fun.
Doesn't look like it's that far out.
Humans are pretty wonderful.
Can't you just hold the button?
So after right about 24 years,
That's
What happened?
that's late
Did it
now.
die?
No, that's 27.
no, there's 1,000 endangered species now, as opposed to 119.6.
I'm pretty sure it's a million.
I forgot what the question asked. It said, estimate when the number of species, so that'd be after 24 years, you could say after 24 years, or if you wanted to say 1996, yeah.
Wait, so we have 24 years or 33? Closer to 1,000, but.
It's pretty close, I mean, after 24 years, you know it happened, if you look at the table,
Okay.
at the end of 23 years, it's almost at 1,000, but it definitely after 24 years
Got
it
it.
was. So
Okay.
this is where, and this is the conversation that we had with Leaf yesterday, where Leaf would be Leaf, and try to figure out specifically like which month it might have occurred by approximating between the two values of how many days are left here and there. Man, I told him to get a job, but, so. You can do that if you really want to get crazy. No. Questions on, what's that? Yeah, you just never saw it because you were over there.
You're welcome.
See what happens when you change your perspective?
So what? You're welcome.
What do you mean, what? What do you mean?
Do those, please.
Now you're
Do those, please. Should be very, very, very easy.
That's the main thing that people.
It's all fucked up.
So when you're simplifying, you just put the negative.
Yes, yeah. Remember, if you're simplifying, no negative exponents, but if you're graphing the negative exponent, it's fine because you're just showing it to tell you to scroll here again.
I don't like doing all of it because
Okay, we gotta go start on this.
You just put two twos together.